rolling.
Okay, we're going to look in this example at calculating the n vector. So this is the same example we looked at in a previous video. We already talked about the graph of this, a helix extending in the positive y direction, a cylinder of radius 3 around that y-axis. And so we've already looked at that, and we already calculated this unit tangent vector and looked at that on the computer to graph. So we're just going to kind of go on with this example and do a couple more steps there. All right, so we want to calculate that n vector, and so we want to use that shortcut formula for calculating the n vector. So t prime, so derivative of t with respect to either t or s, provided we have a smooth curve, divided by its magnitude. Okay, we already talked about that this is a smooth parameterization of the curve, so we should be able to do that provided that the tangent vector changes. So we'll calculate t prime and verify that the tangent vector changes. We obviously wouldn't want this denominator to be 0. So we're going to use this shortcut formula. So we'll calculate t prime, and this is with respect to t, or you can use the dt notation if you prefer that. All right, so in this example that we looked at, our unit tangent vector simplified quite a bit. We had some Pythagorean identities going on in that, and so it simplified quite a bit. And so I wrote my unit tangent vector like this. So I've got constants, constant, constant. Sometimes you might have more variables, and so your derivatives might be more complicated, but the logic is still the same here. All right, so t prime, I'm just going to calculate this derivative. So I'll have negative 3 over square root of 10 cosine of t. The derivative of that constant in the j component is 0. And then here we'll have negative 3 over square root of 10 times sine of t. All right, then that will be my numerator. I need the magnitude of t prime. All right, so after you've done a few problems like this, you might know what to expect here when you calculate the magnitude of t prime and be able to kind of quickly move through this part of the problem, but I'll go a little slower through this one. All right, so I will have this component squared. So when I square the negative, I'll have a positive, so 9 over 10 cosine squared of t. And then this component squared will be 0 squared, which is 0. And then when I square this component, I will have 9 over 10 sine squared of t. So I've got the sum of all those squares and then the square root of the whole thing. All right, so when I do this, because these two coefficients match here, I get some very nice simplification. This term I obviously don't need to write in there. So the algebra there, you factor out that 9/10. This is why it's important that those coefficients match if you're going to do this simplification. Sometimes I see students try to extend this sort of simplification to something where these coefficients don't match. There might be some simplification, but it won't be the same simplification that we're getting here. All right, so because I had the same coefficient there, I was able to factor those out. And then what I'm left with here in this parentheses is the Pythagorean identity. So all of this part here just becomes 1. So I end up with square root of 9/10 or 3 over square root of 10. Okay, so when I go over here to calculate my n vector, I'll take t prime divided by that magnitude. And so I can write this t prime all over this. But especially if we're going to use that to calculate anything else, which we will, you probably want to go ahead and distribute this. Remember that this denominator here will be a scalar, maybe a scalar function. But a scalar, and so distribute that to each component of your t prime vector. All right, so when I take the t prime divided by its magnitude, I'm going to have this component divided by 3 over square root of 10, and notice what happens here. So I will end up with negative cosine t. And then the j component divided by 3 over square root of 10, so that will be 0. And then in the k component, this expression divided by 3 over square root of 10. And so notice those coefficients cancel again. All right, so there's my n vector. Again, I've talked about this in some previous videos. Notice that I've done a pretty good job of labeling my steps here so that I'm grabbing the correct vector. It's really common that I see students do a calculation here and then go up and grab one of the wrong vectors to write this down, especially if you're going to do anything more with that. That just makes everything else after that a disaster. All right, so that's really all we wanted to do for this. We're going to look at it on the graph in a second. Another thing, though, you might just think about, sometimes students get unreasonable answers for here. You know this should be a unit vector. If it's not, you've made a mistake. It should be pretty easy for you to verify that this is a unit vector. The magnitude of this vector is 1. It's pretty easy to calculate that in your head. The other thing that you should know is that this n vector and this t vector should be perpendicular to each other. So sometimes it's helpful, especially if you're going to do something else with this, or if it's a test situation where you want to be sure that you've got the right answer here and you haven't made some careless mistake, would be to check to see if your t and your n is the dot product of those two vectors is 0. So you don't have to do that, but that's kind of a helpful thing to check. So again, make sure you're grabbing the right vector here. Here's my t vector, and then here's my n vector. And so if I look at that dot product here in the I component, I will end up with positive 3 over square root 10 sine t times cosine t. And then in the j component, I will have 0. And then the k components, when I multiply those, I'll have a negative 3 over square root 10 sine t cosine t. And sure enough, that all adds up to 0. So that's just kind of a little handy thing sometimes to check to make sure that your n vector is a reasonable thing that you've written down. It should be a unit vector, and it should be orthogonal to your t vector. All right, I'm going to go over here to the computer, and we're going to look at the graph of that curve. We did this before when we looked at it with the unit tangent vector. So I've graphed the space curve here. You can see the equations. Let me close this window. So you can see the equations, 3 cosine t, t, and 3 sine t. I've graphed that over an interval with a couple of orientation arrows. And then I'm going to go over here to the settings, curve settings, and I'm going to select a few things. I want to see a trace point and a trace vector. Those are selected by default, but I had already unchecked them. The other default settings are that it will show a velocity and acceleration vector, which you can look at too, but we want to focus here on the unit tangent and the unit normal vector to that curve. So I'm going to check those. And then here, when I drag, you can see those vectors there. And so the blue vector, the very long-looking blue vector here, that's the position vector, the r of t, at a particular t value, whatever t value I've dragged this to here. And then you see these other two vectors. Even without labels, you should be able to determine which one's which. The tangent vector is the purple one here, tangent to the curve. That would be t. And the n vector will be perpendicular to that unit tangent vector and always on the concave side of that curve. So notice as we rotate around that curve, that n vector is always pointing inward on this curve. This curve has a lot of symmetry. It's always pretty much the same curve, just rotating around and around. We'll look at some more complicated graphs later where we've got that n vector doing all kinds of crazy things moving around. But the basic idea here is that we just want to think about what that geometry looks like. In the next video, we're going to add in the b vector and look at that as well. And then maybe look at some applications of those.